That's how it works. That system was put in place so you can't get your dream.
Okay, the video is on now. Are we telling people about your dreams?
More than 5 inches taller.
Wait, did you say Mrs. Tyler?
No, it must be 5 inches taller. I had a dream I had a radio in my car.
Sorry, the eight town car doesn't have
So lucky.
Are you guys keeping up with the assignment?
Yes. Me?
No sense you've been asked, right?
Oh, wait, I have a question.
Yeah.
You know, for the first homework,
Yeah.
the first, like, number 1, all of them, like, you know how there was, like, a double and triple, and then there was something, and then it was dx and dy? Is that something representing, like, the 3D portion?
Okay, here. Okay, so the first assignment is in the XY plane. If you have a region, omega, we can compute this area by make a square of infinitesimal width and height. So that would be dx by dy, right? So if you blow it up like this, dx dy. So you can just add them all up, add up all of these squares over omega. And you can choose to go dx first or dy first, depending on the region, right? And then if you have, now you're talking about a 3-dimensional volume then, right?
So if there's
So if you have like a curve above it like this, then to compute the volume, you're gonna do a double integral of whatever the equation of this curve is. It's gonna be z equals something usually, right? So z times dx dy, and then you integrate that over omega. That's an ugly omega. There, that's better.
Okay,
Because then this is gonna be dx dy is this, and so when you multiply it by z, you're gonna get, didn't I draw this picture last time?
yeah, you did.
Dx dy, and then that's z. So that's the volume of the stick, and you add up all of these sticks, and that will give you the volume. So today's lesson is the same thing, except we're gonna do it in polar. So if you have a region,
I remember the cardioid, right?
well, I don't know if this is a cardioid, but. Okay, so the way you guys did it last year is, you guys remember
Yes.
how to do a single integral for this? You go integral from theta 1 to theta 2 of 1/2 r squared d theta, right?
What's R?
The distance
Oh,
from the
what?
origin to the point.
Doesn't it change?
That's what
Oh, that's
Yeah, that's r, that's r. Okay, so 1/2, well, okay, what's the area of a sector? Like this. Oh my goodness. We gotta go back to geometry. How do you compute the area of a sector with angle theta and radius r? Isn't it 1/2 r squared theta? Hey, you have to know this for the trig event this time, you know. Are you in event 4?
Yes.
You gotta know this then.
The trig?
Okay, but this is trigonometry, polar coordinates.
This is polar?
There's triangle, like triangle.
No, but you gotta know how to find the area of a sector. And then arc length is equal to r theta, right?
Yeah.
Oh boy. Okay, but what happens if this angle is infinitesimally small? Then it's gonna be 1/2 r squared d theta. That's what that is. See? D theta r, and then you add up all of these really, really thin sectors from theta 1 to theta 2. That's what an integral does. You just add up an infinite number of things, right? Question.
Shouldn't there be a Friday?
Luckily, I took my medicine this morning.
Oh, cause they.
Okay, let's go way back.
Sorry.
No, too late, we're going back already. What's the area of an entire circle?
No.
Pi, too late, I'm doing it. Pi r squared. Okay, but this sector here is a fraction of the entire circle. What fraction would that be? Well, if you're working in degrees, you would go theta over 360, right? But we're not working in degrees, we do radians, so it's, you multiply by theta over 2 pi. The pi's cancel out, and what do you know? 1/2 r squared theta.
Sorry.
That didn't come up on the worksheet?
It did. I don't think so. Yes, it did.
But like I said, if the angle is infinitesimally small, then it's 1/2 r squared d theta. Okay, but now we're gonna do a double integral. So what you do is you break it up like this. So like over here, you had an infinitely tiny square, right? Dx times dy. But what would the area of this infinitely, I don't know, what would you call that? Let's blow it up. And I don't mean explode it. Okay, like that. How do you find the area of this thing? You can kind of think of it like a rectangle. So this would be like the base, and that's like the height. What would this be? dr, because it's a change in radius, right? Change in r. And this is like an arc length. So wouldn't that be r d theta? Because arc length is r theta, right? From physics or from trigonometry. But what happens when the angle is infinitesimally small? R d theta. So when you have this, it's just dx times dy, but in the polar coordinate system, when you find the area of this thing, it's going to be r dr d theta. So that's what we're going to do in tonight's homework. You're going to have integral r dr d theta. And depending on which one you do first, you integrate over omega. Sometimes, I would say most of the time, you're going to integrate with respect to r first, and then with respect to theta. And then, of course, what would happen if you have like a three-dimensional surface above it? How do you compute the volume of that three-dimensional thing from omega to here? What would the integral become? Then it's going to be like the same thing. You got this thing, but it's like, and then this. So the area of the base is r dr d theta, and this is z, so what would the volume be? Z r dr d theta, and then you integrate over omega again. That will give you the volume. So this one gives you area, this one gives you volume. So just like over here, this is area, but then this is volume, right? Because you're multiplying it by a height. You look befuddled.
Z will be in terms of R and D.
Well, we don't know. We don't know. No, not always. But you have to turn it into r and theta. But that's easy because what did we learn in when we learned trig? X equal r cosine theta. You guys did this last year when you took derivatives, right? Y equal r sine theta, and so forth. Do I have to write all four formulas down?
No.
Oh, no.
No, too late already. R squared equals x squared plus y squared. And too late, tangent theta equal y over x. There, I wrote all four. Okay, let's do an actual problem and enough. We can start watching the movie. The proof. What is the proof about? Redeem yourself, Sam.
The proof?
I believe I sent an email this morning about that, right?
Oh, yeah.
Unless you just like disregard my email. Well, no, just look at me and tell me.
There was like about 11 o'clock, you know. It's about proving this formula that
Yeah, what is the formula?
y equals x.
Proving y equal x. Kaneshiro,
It's Fermat's last theorem.
thank you. And who was the professor's name?
Andrew Wiles.
Whoa, from where?
Oh my God. He's from California.
No,
He's
Princeton.
Oh.
Princeton. I didn't put that in the email, by the way.
Yes, I read it.
Okay, so what would be an interesting, oh, by the way, now I don't know about the people watching the video, but look, one of tonight's homework, you gotta know your polar curves. R equal, on problem number 2, like I kind of told you what it is, but you guys should know from PCH, right? You look at this is a learner, and don't look over there. Okay, I'll give you a hint. Does this sound familiar from PCH? R equal EP all over 1 plus or minus either sine or cosine theta. Oh, I almost forgot something. Forgot the E. Now, what is E? What did we, when we learned conic sections, what is E?
Eccentricity.
Eccentricity. So E is the eccentricity, so in this case, E is 1, right? So when you make this number 1, the coefficient of the sine or the cosine is the eccentricity. So if eccentricity is 1, parabola. Maybe we better write this down. Parabola. I'm just going to put a capital P. If E is greater than 1, hyperbola. If E is between 0 and 1, ellipse. So do we need to review how to graph these? Because you got to be able to graph, you know, to figure out the limits of integration and things. Just say yes for the people on the video.
Yes.
Okay, I'm not going to do this one because maybe I should. What the heck? So you know this is going to be a parabola because eccentricity is 1, right? So, but whenever you have a conic section of this form, what did I teach you in PCH? And I'm sure you did it last year in BC. Plot the quadrantal angles. Oh my goodness. Okay, so plug in 0. What do you get? Plug in 0.
No.
Half. Plug in pi over 2. Pi. Nothing. It's undefined. So already you know it's a parabola, right? And then plug in 3 pi over 2. 1. So then you see the parabola goes like this. Parabola. Okay, let's do another one. R equal, how about 2 plus sine theta? No, let's do a minus. And then wait, 1, 2, 3, 6. Okay, what is this going to be? Ellipse, because the eccentricity is 1/2, right? Wait, before we even move on, does everybody see the eccentricity is 1/2?
Yeah.
Because you got to make this leading coefficient thing here 1.
Yeah.
Okay, so plot the quadrantal angles. 0.
3.
Pi over 2.
6.
Why do you speak?
What? Well, you ask me. Why are you asking him? Ask me.
No,
No, ask me.
I was judging his way of speaking.
Pi. 1, 2, 3. And then 3 pi over 2.
6.
What?
No, that's cat. No,
Those are
no,
groups.
really? No, okay, 2. Sorry.
2. Wait, this is MVC, right?
Yes.
Okay, there's the ellipse. Plot the quadrantal angles, okay? And then finally, how about R equals 6 over 2 minus cosine theta? What am I doing? 1 minus 2 cosine theta. Okay, so the eccentricity is 2, so it's going to be a hyperbola. Okay, plot the quadrantal angle, 0. Huh? -6, right?
Yes.
The 1, 2, 3, 4, 5, 6. Remember, polar, you gotta go 6 units in the opposite direction, right? Pi over 2. What?
Wait.
Oh yeah, 1, 2, 3, 4, 5, 6. Pi.
2. Wait.
Pi, yeah, 2. And then 3 pi over 2.
6.
1, 2, 3, 4, 5, 6. So here we go. We got a hyperbola. So one branch is over here, and the other branch can be over there. So these are the conic sections. So tonight you have a parabola, but on the test, who knows, right? Okay, so let's do, okay, I need to erase because we only can use one side of the board. Okay, let me think of a graph. How about a blob? You wanna do a blob?
Yeah.
Okay, R equals, what does Mr. Ye call it?
Nothing.
So like 3 plus 2 cosine theta.
Did you call it one?
Manapua.
Oh, yeah.
I call it Wanapua.
No, no, it's too
Does
close.
Mr. Ye call it Wanapua too?
What a duck, not one.
Okay, plot the quadrantal angle, 0. 1, 2, 3, 4, 5. I can do this in my sleep. Can you do this when you're awake? Pi over 2,
3,
pi,
1,
and then 3 pi over 2.
3.
See, the placement of this point is gonna tell you what the thing is too. Besides, remember, if this absolute value of that is bigger than that, then it's gonna be the blob or Manapua, right? If the absolute value of that is equal to the absolute value of that, you get the cardioid. But if the absolute value of this is smaller than the absolute value of that, then you get the inner loop. But then you don't even have to know, you just plot the point. See, like, if this number is bigger than that number, this dot is over here. If they're the same, then this dot goes there. If this one is smaller, then the dot goes in here, and that's how you get the inner loop. So just by plotting the quadrantal angles, you can tell. So this one, the graph looks like this. Manapua. See how it kind of flattens out over there? It shouldn't flatten out over there. Okay, I'm trying to think of a problem, that's why. R2. Oh, that would work. Okay, R equal 2. So R equal 2 is, describe that graph to me. It's a circle, radius 2, like that. Okay, so let's do a double integral to compute the area that, which one you want to do? You want to do this one here, or you want to do that one there?
That one.
That one
The
there.
first one.
Okay, A or B? B looks more interesting, yeah?
Yes.
Okay, write a double integral that represents this area here. So I guess outside the circle, but inside the Manapua. Okay, I know the way you did it last year, but you guys got to get into this double integral thing. So double integral of R, dr, d theta. Usually you're going to integrate with respect to R first. So R is going to go, so what you do is you got to think polarly now, don't think rectangularly. So think of the infinitesimally thin sector here. So R is going to go from here to here. So what's the equation of this curve? The inner one, so you're going to go from the inner one to the outer one. 2 to 3 plus 2 cosine theta. And then theta is going to go from here, whatever this angle is, to here, right? You gotta think of the sector here like this. It's gonna go from here to until you get over there. So how do I figure out what that is? Well, you gotta figure out where the curves intersect. So you gotta solve these equations simultaneously. So using substitution, you get 2 equal 3 plus 2 cos theta. Negative 1 equal 2 cosine theta. Cosine theta equal negative half. Hey, that's a number I know. So where would that be? 2 pi over 3 and 4 pi over 3. So is that the limits?
No.
No, because you got to go from here to there. So that's like negative 2 pi over 3 to positive 2 pi over 3. But since you have symmetry, you can just go 0 to 2 pi over 3 and times it by 2 then, right? So you want to do that?
Yes.
Okay, so 0 to 2 pi over 3 times 2. You don't have symmetry all the time, no. All right, now what? How do you integrate this? Well, you got to do the inner one first, right? So what is the antiderivative of r? 1/2 r squared. That's where it comes from. Remember last year 1/2 r squared d theta? That's the d theta. But see, this is just double integral. So the first limit is going to be from 2 to 3 plus 2 cosine theta. Factor out the constant, so you get 1/2. 3 plus 2 cosine theta squared minus 4. And then now you integrate with respect to theta from 0 to 2 pi over 3 times 2. These would cancel out, and of course you guys know how to integrate that. I hand the ball off to you, you can score the touchdown, right? Remember, the only way you can integrate cosine squared is you gotta use the identity 1/2 plus 1/2 cosine 2 theta. Or is that gone from the memory? Okay, but now, what would happen now? Okay, so we have our omega here. What would happen if you have a surface above it? How about a paraboloid? How about a paraboloid like that? What is this? 1, 2, 3, 4, 5. Think of a paraboloid that centered about here, and it's going like that. Somebody give me an equation. So z equals, but I want it to go outside here, so it's got to be like, you know, this is 5, so we want it to be bigger than 5 when, you know, when it hits the, it doesn't really have to be, you can make a smaller one. No, I want it bigger. Come on. Come on. Okay, I'll give you a hint. Didn't we just have a test on quadric surfaces? Okay, what number can I put here so that when it hits the xy plane, it'll be outside this omega region? Gotta be greater than 25 then, right? So give me something. 26. Yeah, but about something like about 36. That way the radius of that circle would be 6, right? Okay, so now we have this. Okay, so what would be the volume of the solid between this omega and the paraboloid? What do you call this? What's the English word? And on the top, it's like bounded on the top by, what's the English word for that? Encapsulating it? Come on, don't look at me, I had a 400 SAT verbal. You had a 400 SAT verbal?
Right, he has to take ELL though.
What does that mean?
I didn't take all four for like 2 times.
Well, okay, well, if you took the SAT, what do you think you would get on the verbal?
No, he took it.
Like,
Would it be higher than mine or lower than mine? So what are you saying? But I didn't grow up in Korea. I went to school in Hawaii. Anyway, so what's the word I'm thinking of?
encapsulate.
The word is cap.
Okay, so let's write the double integral that will give you that volume then. So you got double integral. Okay, z is 36 minus x squared plus y squared. And then r dr d theta. And if you integrate with respect to r first, it's going to be exactly the same. It's going to go from the inner curve to the outer curve. So 2 to 3 plus 2 cosine theta. Now you got to be careful now. Or your omega might have symmetry, but maybe the curve on the top doesn't have symmetry. You know what I mean? So like if it's like a plane, but it's like off at an angle like this, you cannot go 0 to 2 pi over 3 and times it by 2. You know what I'm talking about?
Yeah.
So then you have to go negative 2 pi over 3 to 2 pi over 3. But since we have a paraboloid, which is symmetric, right? We can go 0 to 2 pi over 3 and times it by 2. You guys understand that thing?
Yeah.
So when in doubt, don't rely on the symmetry of omega. Okay, now how do you compute this integral? Mr. Park, what do I do with the x squared plus y squared? Should I substitute x equal r cosine theta and y equal r sine theta? No! Because you somebody, that's r squared, and that's perfect, right, when you're integrating with respect to r. So that's why whenever you see a quantity x squared plus y squared, you know you're going to do it using polar. Because it just makes the integral a lot easier to do. Especially when there's roots. Think about it. if you have to integrate something like this with respect to either x or y, you're gonna have to do trig substitution. That's why if you do it in terms of polar, it's gonna be a lot easier. That's why we have all these different coordinate systems, so that it makes things easier. So do we have to go through this integral, or you guys can finish it? Can, right? So the main thing is you can set up the integral. Because in the videos, I was doing like all the problems all the way till it's finished. But then yesterday when I was doing, I think I was doing double and triple integrals 3. When I got to that third problem, I'm going, why am I computing the integral? Because all I have to do for you guys, I should just have to set it up, right? Because you guys already proved you guys can solve any integral, right? Well, anyway, and I'm telling you, I believe there is a secant to the fifth somewhere in the homework. So from now on, I'm just going to set up the integral for you guys. I'm not going to take it all the way down to the answer. Okay, any questions on this? Question?
Why does it have to be greater than 25?
Oh, it doesn't have to be. But if it's not, then part of the graph is going to go negative. Going to have be in the,
What? 25?
in the, what?
Because that's 5.
It goes
Because this is 5 here, right? Where does this graph cross the xy plane? When you set z equal to 0, don't you get x squared plus y squared equal 36? It's a circle of radius 6, like this.
So keep checking.
So if I were to graph that, the region that lies above this omega here is always going to be above the xy plane here. Because if you make the circle smaller, then some of the graph is going to go to the other side where z is negative. That means some of the volume is going to be negative, which is fine. But I just didn't want that.
How can a circle be on?
That's not a circle, that's a paraboloid. A paraboloid is like here.
Oh.
Here's the point 0, 0, 36. That's the vertex, and it's going like this.
It was less like some would go up and some would go down.
So I just wanted to make something where the whole surface is above that.
Why does it go like that, not like that?
Okay, this is a paraboloid, right?
Yeah.
What does that do? That reflects,
Oh.
no, too late, I'm doing it. That reflects it over the xy plane, and then that will shift it 36 up. Well, I guess in this case. So the paraboloid actually starts there and comes out like this, right?
Yes, if it comes out.
No, but then there's a minus sign, so you gotta reflect it over the xy. So it's going that way, right? And then it's gotta come 36 up. So the vertex of the paraboloid is 0, 0, 36 here. And it goes like this.
So if it was 0, 0, 16, then why would it go beyond that?
What?
Like, you said if it was less than 25. So if it was like 16.
Okay, then it would be 16 here, right? So when it hits the xy plane, then isn't it, so if this is 16, what did you get? X squared plus y squared equals 16? That's a circle of radius 4. That means, okay, here's 0, 0, 16, then it's gonna go like this. See, that's 4 right there. And then it's gonna go to the other side. So part of the graph is gonna be when z is negative. So some of the volume is gonna count negative. Because it's gonna go on the opposite side of the board, this Klein's rule.
Isn't the parabola infinite?
Yeah.
So like.
So, okay, there's the vertex, and it goes like
But
this.
that's just on the-
And it keeps on going.
Like it was.
Yeah,
it
so
would be-
even if it was 36, it will go to the other side.
Yeah, but then.
No, 36, it would stop right there.
Why would it stop?
Because that's 6. Oh, no. 6 is here. So that just means
area of
the
that
entire
region.
graph will be above the xy plane.
Yes.
Not the entire graph, the graph that lies above omega. This is omega right here, this area. The graph that lies above this will be above the xy plane. That way you will get a positive volume.
You like take the point and go to the z value, but like if there was
of less than 25, some of the z values would be negative. Because some of your area or volume is.
Yeah, so like, for example, over here, see, like, okay, here's the point 3,300, right? Or just go 30. What would be the z coordinate on the paraboloid? Well, if you plug in, wait, why are we doing that? We already know it's above. Oh, you mean, what if it was 16? Okay, let's change it to 16. What if we change it to 16? Then here's 4 right here, right? So it's gonna be like coming out like this. So over here, like for example, at 4.5, okay, here's the point, 4.5, comma 0. What happens when you plug that in over there? It's gonna come out negative, isn't it? Because 4 squared is 16 already, right? So like right, okay, here's 4. What happens when you plug in the point 4, comma 0? Into here, what do you get? Don't you get 0?
I think I did one.
But then if you go further, then the z coordinate becomes negative. It's gonna go on the opposite side of the board. But see, you guys really don't need to worry about that. You just, because it's just that some of the volume is gonna be negative. Although, wait a minute. Oh, what if I ask you, compute, don't compute the integral, compute the volume. So you would have to make 2 separate integrals then. Oh, that's a good problem. Why didn't I think of that before? No, I wouldn't do that to you. So that's why it's important to sketch the graph. You guys gotta understand what's happening there. And then even if you don't know what the graph is, look at number 3. How many of you even know what the graph looks like? Z equals sine square root x squared plus y squared. I don't know what that graph looks like. But that's just a surface that's above the unit disk. That's just the z.
Oh, isn't it gonna look like, it's like gonna look like when you drop a water droplet in the water, you know? What is it called? A ripple.
It looks like a ripple?
Yeah. Sine
Oh,
of r.
really?
I don't know.
Or z equals sine of r.
Oh.
I don't know.
Wait, I'm trying.
My first language is Korean.
Sine R.
That's what we did from the project.
What do you mean it looks like a ripple? Punch that in on, what are you doing, GeoGebra?
I use that exactly.
I think I used that equation for my concept project.
Really?
Well, like, instead of z, I did brightness, or like, black.
Oh, your thing that follows the mouse?
Yeah, so then like, it looked.
Can we park must have it already?
Oh, yeah. That's it. What?
No, but then if you expand it like more, like it'll like the two. No, like.
Oh, as you go out, you mean, as you go out?
Oh, yeah,
Oh,
yeah,
yeah.
Oh, that's so cool.
Okay.
Oh, okay, I messed it up. Okay. Oh, that's pretty cool.
Oh, wait, okay, wait. How long is the movie we're gonna watch? We're gonna have to watch it in installments.